Welcome back to the Logic of Risk, episode 14. Before we continue talking about risk measures and probability spaces, I would like to share some news that I think you will enjoy. Thanks to an idea from a listener of this podcast, our friend Wissam, all the scripts of the various episodes have been collected into a single dynamic file that evolves along with the podcast. You will find the link and all the info at thelogicofrisk.com. Thanks again, Wissam, and I hope I have pronounced your name correctly. Now, let's return to our discussion, and in particular to the question we ended with in the last episode. What's a sigma algebra? Given a set, such as our sample space omega, a sigma algebra or sigma field on omega is a family of subsets of omega that satisfies a few properties. Three properties, to be precise. First property, omega itself is in the sigma algebra. This is clearly true for the event space if it contains all the subsets of omega, including omega itself. Second property, closure under complementation. This means that if I take a subset of omega that belongs to the sigma algebra, then its complement also belongs to the sigma algebra. For example, if I roll a die, getting an odd number is an event, and getting an even number is its complement. If the event space is the power set of omega, as we said last time, closure under complementation is trivially satisfied. For every event defined as a subset of omega, its complement is also a subset of omega, and hence part of the event space. This is also true in the case of the certain event, namely the entire sample space. In fact, the event space includes the null event, that is, the empty set, which is the complement of the certain event. In the roll of a die, the certain event is that one of the numbers from 1 to 6 appears. The null event is that nothing comes up when I roll a die, which is clearly impossible in our idealized game where a face must necessarily be revealed. Third property, closure under countable unions. The third property tells us that the countable union of elements in the sigma algebra defines a new event that belongs to the sigma algebra. Countable union means it can be an infinite union as long as it can be indexed by the natural numbers. Simply put, if I take events from the event space and combine them by taking their union, say in a set containing A, B, C, I take A and B and unite them into AB, then that pair belongs to the event space. If the event space is the power set, this is again trivially true. Just as the sample space is usually called omega, the event space is usually called capital F, writing the capital letter in cursive. The pair omega capital F is collectively called a measurable space. Why measurable? Because it represents the minimal structure on which we can mathematically define a function that measures its components. For us, this measure is probability, the probability measure, which we call capital P. Probability is therefore a function that takes a subset of omega, that is, an event belonging to capital F, the event space, and returns a number between 0 and 1, interpreted as the likelihood of that event's occurrence. We require this probability function capital P to respect the axioms of probability we listed when introducing the axiomatic definition. Hence, capital P will assign the value 1 if we consider the certain event, the value 0 if we consider the null event, and something in between for every other possible event. This function also lets us calculate the probability of a complement event as 1 minus the probability of the original event, and it can handle countable unions of mutually exclusive events. The key here is sigma additivity. In a sigma algebra, like the event space, we can consider countable unions of events, and we need probability to accommodate them. Okay, important remark. If the event space does not coincide with the power set, as we are assuming here, but is rather a proper subset of it, we are not automatically guaranteed that such an event space is a sigma algebra. We would have to verify it in order to work with the standard axiomatic definition of probability. If you recall, I also mentioned that for Definetti, sigma additivity makes no sense, and that finite additivity is preferable. In that case, we would not need sigma algebras, but algebras, where only finite unions of events must remain within the algebra, without worrying about infinite unions. Essentially, nothing else changes. This has roots in Definetti's more subjective approach, where probability focuses on personal degrees of belief and depends on our limitations, such as our inability, given our limited amount of time on Earth, to count to infinity. Again, for Definetti, probability should not depend on the possibility of handling infinite collections. But let's come back to the standard axiomatic approach. So again, capital P must satisfy the three axioms of the axiomatic definition. The exact details, whether probability is objective or subjective, are issues we will set aside for now, because all the definitions we have seen so far are valid. It is not so much the mathematics that changes when going from one definition of probability to another, but rather how we interpret the different quantities. We will revisit these questions in more depth when we look at applications. If omega capital F is a measurable space, then the triplet omega capital F capital P is called a probability space, and that's all we need to start formalizing risk. A probability space is the starting point for our calculations. In fact, starting from the probability space omega capital F capital P, we can define random variables, and these random variables will be the tool we use to represent any possible damages or losses, which we then measure with risk measures. What is a random variable? Put simply, it is just a quantity, mathematically a function, that can take different values depending on different random events. Take the toss of a coin. We could define a random variable, which we call x, that takes the value 0 if tails comes up, and 1 if heads comes up. If the coin is fair, we can say that x is 1 with probability 1/2 and 0 with probability 1/2. In this case, x is a discrete random variable because it can take on a finite number of values, 0 or 1. A variable is called discrete if the number of values it can take is finite or countably infinite. Specifically, our x here is a Bernoulli random variable, meaning it takes two values, 0 and 1, each with a given probability. The equally likely scenario, 1/2 and 1/2, is just a special case. More generally, a Bernoulli x might be 0 with a probability p of, say, 70%, and 1 with a probability 1 minus p of 30%, or 15% and 85%, and so on. Other examples of discrete random variables include the binomial, de Poisson, and categorical quantities, among others. Consider the number of emails you receive in a day. These can only be 0, 1, 2, 3, and so on. Whole numbers. You cannot get 1.7 emails. So, a random variable describing the number of emails you receive is definitely discrete. If a random variable can instead take a continuous range of values, we call it continuous. Examples of continuous random variables include the normal, the exponential, the Pareto, and the log normal. The time you wait at a bus stop can be 3.2 minutes, 10 minutes, 5.17 minutes, or any other real number in an interval. So, in this case, your random waiting time is a continuous random variable. But we can make it discrete if, for example, we count only whole seconds and ignore smaller divisions of time. Why do we need random variables? Simply because they allow us to be more flexible and to use more powerful tools, namely risk measures. Mathematically, it is not very practical to work directly with heads and tails, or with broken bones, lost work hours, number of infected individuals, power blackouts, feelings of sadness, or any other random event in its raw form. These events are better handled if we represent them by variables that take numerical values we can add, multiply, divide, transform, and so on, making it much easier to do calculations and analyze scenarios. A coin toss, for example, always represents the same phenomenon, but by adjusting the random variable x associated with it, I can decide that tails is 0 and heads is 1, or tails is -1 and heads is 2, or any other values I find useful. So I can start with the same real or imaginary random phenomenon and use it to describe different situations. For example, we will see that a Bernoulli random variable can be used to study the default of a company as well as my chance of winning at the casino. Once I define the most suitable random variable or variables to represent the potential damages or losses I want to protect myself from, a risk measure allows me to study those damages, those losses, to analyze them in depth, to quantify them, and to prioritize them. For instance, I can ask myself what the expected loss might be, and then consider whether that average is really representative of the situation. After all, I can get an average of, say, 10 from 9 and 11, but also from 0 and 20. And if 9, 11, 0, and 20 represent millions of euros in losses, or the number of people injured in a disastrous event, there is a clear difference between these situations, even though the average is the same. So, we shall see that the right choice of the right risk measure is of paramount importance. I can also ask with what probability I might face the worst potential losses, thus focusing on what we call the tails. Especially in fields like natural disaster management or certain areas of finance, damages and losses often follow sub-exponential, if not fat-tailed distributions, such as the log normal or the Pareto. These imply that extremely large losses, though rare, can happen more frequently than a normal distribution might suggest. That's why looking at the tails of the distribution is crucial for proper risk management, as we will soon see, so don't worry, we will be back. I think today's episode is already quite dense, so it seems wise to stop here without overdoing it. Please stick with it. I encourage you not to give up listening. Perseverance is key. It can take time to absorb some of these concepts, but I promise that in time everything will become clearer and we will repeat anything that needs repeating. Moreover, now you can also rely on the written text, and on the logicofrisk.com you will find a summary slide. In the next episode, we will delve a bit more into random variables, for instance by talking about probability distributions. We will also refine our discussion on risk measures, which we will want to have certain desirable properties for effective risk management. Today, I recommend a little book by Darrell Huff that is both useful and fun. Its title is How to Lie with Statistics. Finally, today's closing quote is from Warren Buffett, the Oracle of Omaha, the famous American entrepreneur, investor, economist, and philanthropist. Someone who definitely knows a thing or two about risk. Quote, only when the tide goes out do you discover who's been swimming naked. Unquote. With what we will see together, we will try to at least wear a minimal swimsuit. If wetsuits are out of reach. Nothing against naturism, of course. As long as it is a conscious choice, it is awkward to swim naked if you are then ashamed about it. Ciao ciao!